You're rolling.
I don't have anything on the monitor here.
You're still rolling.
Okay. I'm going to make an introductory announcement. Before turning the floor over to Nancy Wogren. I would like to solicit your creativeness and innovation for some help. So we'll have a little contest. I'll explain to you what the problem is, and then solicit suggestions. If a suggestion wins and is used, what you win is a free copy of the real book, of which the mimeograph version is what you have right now, when the real book comes out at the end of August. Well, let me explain what the problem is. Imagine that we wanted to create a one-page flyer for that book, of which the front part of the flyer is the normal information, title of the book, authors, publisher, that sort of thing. And the rear page of this one-page flyer is something from the book or representing the book that will make someone want to hold on to this flyer until August. In other words, something really valuable that's on the back, so that they'll post it on their bulletin board or keep it on their desk or in their drawer, and then come August, they'll still have this flyer around to remind them that the book exists. Okay? Now the question is, what should we put on the back of this flyer? What information that is either in the book or can be summarized from the book or in some other way represents the material in the book should we put on the back page of this flyer? We're looking for good ideas about that. So I'd appreciate any suggestions that you have. I know that Nancy has a lot of announcements to make about handouts and textbooks and all kinds of things before diving into her lecture. So I'd like to turn the lecture over to Nancy Wogren. Nancy is a master's student in the Artificial Intelligence program in the Computer Science Department, but much more to the point for this course, she's an experienced, very experienced teacher of expert systems and knowledge engineering at Digital Equipment Corporation, where she's an employee. Nancy Wogren.
I get it. That's okay, I think. Okay, first a few announcements. Can we have? Thanks. It's a little small. First of all, the phone for the office hours was wrong in the handout. Number 7231997. Has anyone tried to go to office hours? I know that no one has gotten to office hours, but maybe someone has attempted and not found their way. We're so lonely over there. If you have any problems, let us know. The reading for Thursday has been announced several times. Bob Flast from American Express is coming to talk about their system. And for that session, it would be helpful if you read from The Rise of the Expert Company, the chapter on American Express. I'm not exactly sure which one that is. Chapters. Many sections in each chapter. Okay, so now I have question marks by this because apparently there is some trouble finding this at the ASSU, and I thought maybe Nabil could speak to us about what the situation of those books was.
What's the situation of the book?
A number of students have said that they've tried to get it at ASSU, and either they don't know what the story is, and Godot brings
in the
them back
ASSU
out.
there is several offices, and there is one office deals with copying and text editing, everything. At that office you will find the book. I will try to get the exact name for that office in the second floor. In that,
I don't know when we'll do it, but we'll do it.
Maybe they run out of the copies because I gave them estimated number for the number of students 50, and it turns out that there is now 70. So I will check with them, but it should be eventually be there. I will check with them and make sure that they have it in the second floor.
I have heard that after 4 today, so one student said that that's what they told them. So sorry this is such a hassle, but just keep trying. Eventually you'll get it. Past handouts. Some students have asked, we had this on one of the original handouts, but if you don't have an original handout, it's hard for you to know this. All handouts, after they're handed out in class, will be outside of TAC, which is in Tressidor. If you go into LOTS, that huge computer room, in the back right corner is an area called TAC. And there's boxes outside of that, and one of them for 408. So you can get past handouts there. If you are new to the class and you have not yet signed a list, see Nabil after class, and we'll get your name and department, et cetera, et cetera. Any other course questions, administrative type questions? Okay, let's begin. Okay, the lecture for today is on an overview of the expert system technology. Now this class doesn't have any prerequisites, doesn't require that you're computer science or that you've had other courses in expert systems. And that's not really the concentration of the class. We're not going to teach you how to build an expert system. But without that information, there's something missing. And so what we're going to try to do is, in this class and next Tuesday's class, try to cover the guts of building an expert system. So necessarily it will be brief, but we're doing this for 2 reasons. One is that we don't want you to feel cheated. We want you to have a sense when you're listening to these people that you really know what it is that they're trying to accomplish. And secondly, we expect you to know it. So there's a number of good readings on it, and we have those in the handouts, as well as I will talk about a couple of them that I think are particularly good today. And also, we'll have in the videotapes, there are some which deal explicitly with how to build. And so in those, you'll also learn how to do it. Also, I encourage you to use office hours for that, because certainly if you have some questions about how they were built, talking about them is one way to get that in. Now, as Ed said in one of his first lectures, there are only a few elements that you have to learn, the basis of this technology. And that's why we think that one lecture is going to be enough to cover it. So that's what we're going to do today. Okay, from what Ed said, we have this. From what Ed has been talking about, there's one principle behind expert system development. And that's captured in the slogan created here at Stanford, "In the knowledge lies the power." And what the idea behind this slogan is that you can solve problems, complex problems in highly specialized domains, by collecting knowledge, by a collection of a large amount of knowledge in that domain. Well, the key to doing that, at the bottom of the slide here, is knowing how to represent and use that knowledge, how to reason with that knowledge. And so that's what we're going to talk about today, is how knowledge is represented and how reasoning is done with that knowledge. More specifically, what we're going to talk about today, I have them down on the slide again, thank you. What we're going to talk about are the most common knowledge representation and reasoning paradigms. And we're going to restrict this to commercial expert systems. A lot more is being done, but is still restricted to a research or an academic location. So what we're going to look at is what is in those tools that are being sold by all those nice AI startup companies. We're also going to consider some of the essential capabilities of expert systems, uncertainty and explanation. And the bottom line of this, though, or one of the bottom lines, is that I want you to see why people use tools. Why don't people just pick up BASIC or Fortran and write their own expert system in it? Why would you need some specialized tool that costs $1,000 or hundreds of dollars? Okay, what we're not going to be talking about today is I'm not going to be describing the tools. I'm giving you the technology behind the tools, technology that you'll see over and over again in the tools, so that you as a consumer could look at those and tell what's inside. You can say, ah yes, that's a X, oh that's a Y. And we're also not going to talk about how to choose the right one. Paul Harmon will be here later in the class, and he will talk about the tools themselves and how to choose them. We're also not talking about the steps in building an expert system, and we'll hold that off until next week. Not talking about how to choose an explanation. I think an application that comes next Thursday. And implementing a user interface, although it's very important, there aren't a lot of, there's not a technology behind that that's different than user interface technology in other fields. I'll say that it is very important and growing increasingly important, particularly with the use of graphics today, and a system only appears as intelligent as the user regards it to be. So being able to use the system easily is clearly very important. Okay? If this hasn't satisfied you at the end of this lecture, you still don't feel like you really understand what the main points are, there's some further reading you can do, and these are my favorite references, and strangely enough, they're some of the oldest references in the field, but I think they still are those that capture what's going on the best. And there's Building Expert Systems, and all of these, I believe, are on reserve in the library. Building Expert Systems, Rule-Based Expert Systems, which is about the Meisen system built here at Stanford, and then the Handbook of Artificial Intelligence, which is 3 volumes. And you'll probably find the first volume, which covers knowledge representation, and the third volume, which talks about expert systems, the most useful. But what's nice about this book is that inside the front cover of each volume, they have the complete index for the 3-volume set. It's really easy to find your way around. But my bottom line message is that reading isn't really going to do it. The nice thing about expert systems is that they're really fun to build. And that's why it attracts a lot of people into doing it, because you don't really get the sense of the power that you have there until you've tried it yourself. And I think that the tools are available today so that somewhere in your life you could probably find one and use one. Even if it's only to get a demo, to go down to a local computer store and find out what kind of expert system software they have, although it's more fun to use it yourself. So I really recommend doing that. We're not requiring you to do it, but with a little ingenuity, you could probably find one and use it. So I really encourage you, because otherwise it gets a little dry. You don't really get it until you've put some rules in and suddenly they're doing this thing. It's like, I guess using a spreadsheet isn't quite a good analogy. It's not quite the thrill. Okay, so we're going to start off talking about rules. By far the most heavily used in commercial expert system building tools today. First of all, I'm going to start out with just the anatomy of a rule so that I can use some terminology later on. A rule has 2 parts. It has an if part and a then part. Sometimes these are called when and do, so that people don't think of them just as their control structure counterparts in traditional languages. In the if part, also called the left-hand side and abbreviated LHS, are a conjunction of conditions. All of those conditions must be satisfied for the rule to fire. And the right-hand side are a series of actions, and that's called the right-hand side. Okay, so that's it. That's it for a rule. That's as tricky as it gets. Now I'm going to talk about rules from 3 perspectives, because the truth is that people use rules in different ways. And so I'm going to give you 3 perspectives on rules as conditional statements, and that's what you're familiar with in traditional languages. Traditional, conventional, there's something wrong with those terms, but I can't think of better ones. As deductive implications, and also as search operators. And I'll talk about the final one. I think that's an important way to view a problem when you're doing expert systems. Now, in most commercial tools or in most languages that use rules, rules are used in all of these ways, and it does not, you as the builder do not have to be conscious of the different ways that you use rules. So I'm just trying to give you a few different perspectives of looking at what's really behind a rule. Okay, so first of all, rules as conditional statements. My head is blocking this. Thank you. Okay, now expert systems are ill-structured problems. And Ed has been talking about how what these systems are doing are solving problems in which there are lots and lots of alternatives at each step. More alternatives than you could possibly keep in your head, and a lot of reasoning that is uncertain. It's not, you cannot capture this in one generally applicable algorithm. You can usually think of lots and lots of exception cases, and that's why it usually requires an expert, someone very, very proficient in the field who knows what to do in all of these exception cases. And these are called ill-structured problems as opposed to well-structured problems. Well-structured are the algorithmic approaches you can use in your basic Fortran and C programs. Okay, but in order to handle these special cases, we can use rules. And rules are just analogous to the if-then-else statements of traditional programs. So for example, and I hope that I don't draw on this too often, but the XCON or R1 system from Digital, that's an ill-structured problem. In an average order, there's something like 50 to 150 components that go into making a computer. For each of those components, there can be up to 125 or 150 different aspects of that one component. There's properties of that component. If you put that together, we have something like 10,000 pieces of information. Now each order, when you configure it, has something like 1,000 steps in configuring. So we're talking about a lot of information. Here's a condition action rule from XCON, and this is of course simplified and in English. But they say things like, well, if there's an unassigned dual port disk drive, the type of controller requires is known. And by the way, that you should notice that this is a little bit, this is control information here. So you know that you're talking about a disk drive, and somewhere else in the program, you've already figured out what the controller for that is. That's why I call it control information. And here I have two controllers, which is how many I need, and they don't have devices assigned to them yet. And I know how many. This is also done somewhere else in the program. So why I'm saying these are controllers, somewhere else in the program, I've already figured this out. So the number of devices that these controllers can support is known, or so other rules do it, not other parts of the program. And then what I'm going to do is assign the disk drive to the controllers, and then also make some note to myself or to the system that each controller supports one device. Okay, so this is one rule in many. Now, if you think of your favorite language, and if you were going to write an expert system in there, one way you could do it is just have a series of if-then statements or if-then-else statements. Anyone think of why you might want not to do it in BASIC or Fortran? Why don't you use the mic?
The nest structure would get incredibly deep, and it'd be tough.
Yeah, you'd have to nest pretty far. You'd have if then else, if then else, if then else. Any other ideas? Well, if this is your basic construct, well, first of all, if you're going to do it in if then else, you're implying some order of firing of the rules. Because what if you find the if statement that tells you the right thing to do? Are you going to have to start up at the top again and go through each one? So there's an efficiency consideration, which is in fact how some rule-based systems are implemented. But it makes sense if you're going to have a program which is based on one construct alone, that you put in some special mechanisms for dealing with that construct, and rather than try to make something that has a whole bunch of other features in it, it makes sense to do this specifically for if-then. And we'll look at what some of those constructs are. Okay, rules as deductive implications. Well, this is something that they like at Stanford. Well, really what a rule is a logical state, a logical implication. And if you make sure that your actions are only adding, and in some cases removing things from your database so that things stay monotonic, and that the facts that you conclude are always logical consequences of something that went before, well then you have nothing but logic there. And you use modus ponens to chain the rules. So that you have, if you have some statement A and you know that A implies B, well then you also have B. And this is the idea. Unfortunately, when you're talking about complex domains, this really isn't strong enough to cover the fuzziness. So not every implication that you make is going to be logically correct, or it's going to be a logical implication. And consequently, most expert system tools are not built on logical deduction techniques, such as resolution. Prolog, of course, is the stalwart example of using logic, but even that has some, particularly as it gets more usable, has some side steps around strict logic. And finally, you can view rules as operators in viewing an expert system as a search problem, or an ill-structured problem as a search problem. If you review something as a search problem, what you're saying is that you have, or one way of conceptualizing it, is that you have a series of states, of discrete states that you go through to bring you from some initial state to some final state. And a state is just a snapshot of the world at a particular time. So if I start here, and I'm in an ill-structured problem, so I know that there's lots and lots of states I can go to from the next state. What I'm looking for, this is often represented as a graph problem. What I'm looking for is a way through that graph to my goal state. Okay, so each of these are states. It's some description of the world at one point. And the state space, and I'm introducing this only because you'll hear about the state space formalism if you talk about search. And the state space are just all the attainable states that you can get to in that problem-solving domain. And the operators are what transform one state to another. So if you think the search process is the process of finding the set of operators that take you from the initial state to the goal state. So if I have one operator number 1, one operator number 2, and another 3, then my solution is going to be 1, 2, and 3. Those are the 3 operators that I apply. Now if I use rules as operators, rules are smart operators, because in their left-hand side they give you information about what state they apply to. And so in the left-hand side, it says, this is the condition, and I have that down here. These are the conditions of the world that exist when it's time for me to do my job. So rather than having to apply operators and then check the states that are the result of applying that operator, what I can do is just use rules when they say they apply. And when you're writing rule-based systems, one of the tricks is knowing how to specify in the left-hand side what the world looks like when that rule is supposed to fire. If you specify it too tightly, it's not going to fire in all the cases that you want it to fire. If you specify it too generally, it's going to pop up when really that's not, it wasn't supposed to fire right then. So this process of state is a very useful way of thinking about what you're doing with rules. You're changing the state of the world from one state to another. And we'll see why that's true in just a minute. Okay, so you have this set of rules. And now you want to use these rules to solve a problem. Well, there are 2 ways of thinking about how you're going to solve a problem. And humans don't have to consciously decide which way they're going to use, but in fact do some meshing of the 2 of them. But you can either go forward from your initial state to some goal state, or you can go backwards. You can start from the goal state and say, this is what I think is true. Let's see if that in fact is true. Let's see if the data that I have on this problem really bears up to that. So there are so when do you do forward chaining? You do forward chaining when you have all the data that you need to begin with, and it doesn't make sense really to hypothesize a solution to direct your search. So for example, XCon, it doesn't make any sense to put together a computer and then say, now is that the right computer? Because it would be so hard to put the computer together in the first place. Well, how would you have found that? So instead, you start with all the components, you start with the database, the constraints that are on putting those components together, and you fit pieces together. At each step that you make in applying a rule, you say, well, what is the next possible thing I can do now? And in forward chaining problems, all you know is you'll know it when you get there. Okay, so forward chaining problems can thrash without correct knowledge. Backward chaining, on the other hand, you don't have everything you need to begin with. And it's impractical, in fact, to get all that information to begin with. So the prototypical backward chaining problem is a diagnosis problem. You're not going to bring a patient in and ask them every single thing you might need to know about them in order to diagnose. You only want to diagnose based on some hypothesis you have about what might be wrong. So you find a little bit about them and you form a hypothesis, and then you go and ask them questions specific to that hypothesis. So each step in the backward chaining process, you're asking the question, what do I need to know to confirm this hypothesis, or to confirm the step I'm in right now? Okay, and as in the Buchanan and Smith article, when they're used together, they call this opportunistic. So you can use some basis of information to generate a hypothesis, and then use, that's forward chaining, and then use backward chaining to, in fact, substantiate the hypothesis. Okay, some examples, and this is right out of the Waterman book, but I think that using this simple, I need it down here, thank you. Using the simple atomic elements of a rule and of a database are really helpful. Let's say we're looking for the conclusion Z, and we're going to do this in forward chaining. We have 3 rules in our database. What do we do if we're for a forward chaining system? Well, we don't care about what our final state is. All we know is that when we get to our final state, we'll know it. So we actually have some kind of recognizer of our final state. So instead, what I do is I'm going to say, well, how about the first rule? Want to fire that? Well, if I look up to my database, I have B, but I don't have F. So this rule does not apply at this time. Go down to the next one. Well, for this one, I need C and D. Thanks, that's great. Okay. And I have C, don't have D. This rule doesn't apply now either. Go down to the final step, and I say, well, do I have A? And in fact, I do have A, so I'm going to fire that rule. When I fire that rule, it produces D, and now I have a new state of the world, and now I'm going to try again. Do I have F and B? No, I don't have F still. Do I have C and D? Yeah, I do have both of those now, and so I can fire this rule. Notice, in this system, I actually also have the rules for A. Most systems have some way of saying, don't fire that rule again if you've already done it, or I could actually, in fact, remove A after I've fired that rule. But now let's fire this rule, and so when I fire a rule, that means I do whatever is on the right-hand side, and I'll put F into my state of the world. And now, in fact, if I start again, I do have F and B, and so I'll fire that rule. I'll get Z, and now I recognize, that's a solution, and I can stop. Okay? Let's do the same problem using backward chaining. Okay, so I'm looking for my conclusion Z, and this time I'm going to use the conclusion to guide me through the problem, though. So instead, I'll say, well, what I'm looking for. So I'll look on the right-hand side. What I'm looking for here is Z. Well, in order to get Z, I'm going to have F and B. Well, I have B, but I don't have F. How could I get F? Well, I'll look back here. Well, this rule here concludes F. How am I going to get F? Well, I need to have C and D. I have C, don't have D. How am I going to get D? Sure enough, there's another rule that gives you D. And so the first thing I'm going to do is after having gone through that process, I'll fire A, which gives me D. I'll fire C and D to give me F. I'll get F and B. So you'll notice the solution to these 2 problems, lo and behold, turn out to be the same, and yet we used a different process to solve it. What might I have to do to change these to make, this was pretty clear. I wouldn't know how to choose which was really the best method to use, forward or backward chaining, to solve this problem. What could I do different? What would be different about the state of this problem if I were going to do it in forward chaining and not do it in backward? How about the other question? What would be true about this problem if I definitely didn't want to do it in backward, or definitely not want to do it in forward? What if I had a whole bunch of rules? Lots and lots of rules, and they concluded all sorts of different things. I really wouldn't want to go about forward chaining if I had lots of things to do on this. I could endlessly fire rules that wouldn't really get me anywhere, because in this problem where I have there's no information in this, there's no control information, and I don't know what I'm doing step by step. Does that make sense? Anyone have questions about forward and chaining back rules?
Yes, in this case, you assumed that you wanted Z, which happened to be the correct answer.
Right.
What happened in all the other cases where you had chosen the wrong answer as your assumption?
You would have to hypothesize again. You would have to then try a new solution. So, for example, if I'm a doctor and I say, gee, I think this is fever, and I'm going to go back and try to find, no, I don't think this is fever. I think this is such and such a disease. So I look to see how much conclusive evidence I have. Now I can look at a couple different hypotheses at once and then compare what strength I have for different hypotheses, or I can do them individually. But you can never restrict yourself to, I only know one. Okay, and in forward chaining problem, you don't necessarily know exactly the solution when you get there. It's not as though you said, oh yes, I knew that ahead of time. You'll know what properties that conclusion has to hold to. Okay? Okay, that's forward and backward chaining. Okay, so we have, how do we use these rules together in a program? Okay, well, the components of our rule-based language. Now, notice that this is different than what Ed was talking about. What are the components of an expert system? And I think he said knowledge base, database, knowledge base, inference engine, and user interface. And here we're talking about the language itself. So this is one level lower on abstraction. So in this case, we're going to have some set of rules. And these are just if, then, if, then, if, then. We'll have a bunch of data. And this is like the pictures that we had here. And then we have some inference engine that makes it all work together. And so what this inference engine, or sometimes called rule interpreter, does, first thing it does is it has some kind of a way of matching the rules to the data. So the rules know what the state of the world are at a particular time. This is the match process. From the output from the match process is either a rule or a set of rules that are eligible to fire. And from that set of rules, if it's a set of rules, then I've already selected a rule, and then I could just go ahead and fire. If it's one rule, I've already selected my rule, and I just go ahead and fire it. If I have a set of rules, I have to go through a separate step called conflict resolution. And what that means, it says all of these rules are applicable right now. How am I going to choose one rule from that set? Okay? And when you choose that, then you fire. And why this points back at the data is because most rules somehow affect your database. So it changes the state of the world. Some rules don't. You can actually have rules that have some kind of I/O function or an external routine. And so those rules probably won't change the match for the next step. But if you have some kind of conflict resolution, you had another rule to fire anyway. But most rules actually change your database and when you execute them. Okay, so that's really what a rule-based system looks like. Now, in implementing a rule-based system, what do you need to know as a programmer? Now, these implementation considerations are not considerations that you would use in choosing a tool. These are things that you're going to have to learn as a programmer as you learn the tool. And most people learn these without knowing what they're learning. And so I'm just going to make them explicit for you. One is that you have to understand how pattern matching works. You don't have to know how it works. You have to know what patterns you're capable of specifying. So what does a pattern look like? Can you use a frame as a pattern? And we'll talk about that in a little while. What does a feature look like? What does a value look like? Can you use variables? can I talk about a value in my database? This is using variables. Can I talk about a value without actually specifying what that value is? Can I just say, if I have something X and it's greater than something Y, can I just talk about things, talk about some general class of values? I also have to know what my matching operators are. I mean, one way you can do match, or a simple way, is either they're going to be, two things can be equal. Can I also talk about, I want to specify that data is greater than or equal to, or that I want it to match to one of several options. So there's a disjunction of possible matches. You have to know what kind of matching operators are available to you. Some systems are very simple. The pattern that they specify is just a list of atoms, and how they match is they match to literally the same pattern in data. You also have to know how conflict resolution happens, or how a rule is selected. If only one rule is selected at a time, how does it select a rule? And it always surprises me that documentation on these tools is not always explicit about how that's done. That's supposed to be, I don't know what they think. You somehow have to figure out how they're doing that. Some of the possibilities, some of the common strategies, is that you can just take it by rule order. First rule up wins. First rule that's satisfied wins. There's some software engineering problems with this technique, as you can imagine. What happens when you change the order? How do you know if an engineer put something in that order for a specific reason? Can you change it, or will that change how the program executes? Rule order isn't a very nice way if more than one person is going to be working on the program. You can talk about the recency of the data that matches a rule. If I have a lot of recent data matching to that rule, that must mean that this is sort of my focus of concern right now. This must be the problem that I'm in the process of solving. You can have priorities associated with rules, something I also don't like. You can say, this is a top priority rule. If this rule is instantiated, which is what it's called when the data matches to the rule, if it's instantiated, fire it right now. Well, I mean, that's saying I'm just going to number my rules and tell you when to fire them. That works. The priorities has the same problem, the software engineering problem, as the rule order. How do you know when you're writing a rule that you assign a priority that doesn't get in the way of somebody else's priorities? And also, another conflict resolution strategy is how specific is a rule. And the assumption there is, if you have a very specific rule, that's probably going to be more important to fire than a rule that's a very general case rule. The other thing that you have to know in implementation are what are the effects of rule firing. And most systems just have a handful of actions that you have to learn, 10, 15 actions that you can do on the right-hand side, and what happens when you do that. So that's straight syntax. Okay, so those are the things you have to learn about your rule-based system. When are you going to use rules? Maybe I should have put this first. Well, I'm going to choose rules when I don't know the algorithm for solving the problem, when I know that there are heuristics for solving the problem, and I can talk about the heuristics to the person who knows it. I can actually get from them a set of if-then rules. I can ask them actually to talk about their problem that way. Problem solving is symbolic. We're not talking about comparing numbers. We have this great capability of pattern matching at our hands. We want to use it. We want to be able to talk about concepts just as names of things, and the relationship between concepts also as names of things. And we want to make sure that that we don't have to have an optimal solution. We're not talking about numbers here, and if we're looking for optimality, we may fall short by using heuristics, which are good guesses and not sure bets. And this is a very digital-oriented criteria, and that is that the rule base is growing or changing. And so some people make the argument that actually XCON is a very sophisticated bin packing problem, and they have hired mathematicians who, in fact, gave them the algorithm. The problem is that digital is putting out new equipment at a very, very fast rate, and in order to put that into the algorithm, you have to have somebody madly trying to incorporate these new architectures and new elements into the configuration of a computer, which is not an easy task. It is somewhat easy to talk to an engineer and find out how does that fit with the system. And so digital, for particularly the first and the last, has a philosophy that if you don't know the algorithm, even if you might discover the algorithm, you can use rules to find out or to work with the domain before you know the algorithm. And also if it's a growing or changing problem, and we'll see why this is, and I'm going to try to substantiate this claim. There is this advertised claim that the reason that rules are so good is that you can add rules and take rules away and with no effect on the system. And I'm going to try to substantiate that a little bit. Okay? It's very quiet out there. Feel free to ask questions. Okay, advantages of using rules. And these are somewhat from a software engineering perspective. The advantages are that you can having rules incorporate representing this heuristic knowledge, and having an inference engine, which you can really call your control knowledge, because that's telling you what's going to fire next. You've separated the two of them. Okay, so rules are just these. They're just jewels of information, and because there's no information in a particular rule about what rules fired before and what rules fired after, except by explicitly referring to the state of the world. If you take out a rule, it's not going to suddenly stop when it comes to the place where that rule was supposed to sit. It's not like taking out a call to a subroutine, where if it doesn't have that call, well, what does it do next? You have to put in new control structures to tell it how to get around it. Well, you don't have to do that in a rule, because that's not where the control sits. It doesn't sit inside of a rule. So you might not get exactly what you expected when you take a rule out, but you will get something. You're not going to have any compiler errors, and you probably will run through. Get a different answer, might not be right, but the program tends to degrade a little more gracefully. So the other advantage of this is that for the most part, a programmer doesn't have to think about control structures when they're programming. So if you have a lot of people working on a project, you can give them specific tasks and say, just make sure that all of your rules work together in this little pocket of this small subtask of the problem. And within that, they don't have to worry that that there's control information in there that fits in with the rest of the program. Another advantage to using rules is that we're talking about getting information from human beings for the most part. And to do that, you're going to have to, and we're going to talk about knowledge acquisition next Tuesday. To do that, you're going to have to try to figure out what somebody else knows. This representation tends to be very intuitive to humans. And you can say to them, if such and such happens, what do you do? It's not like saying to somebody, so if I have, while I is equal to 1 through 10, what do you do? It's not the same, it's not asking to them to make the same conceptual leap. So the other advantage of this is not only for a programmer's ability to get information, but also because this hopefully is we're going to take the middleman out, and the expert, if computer inclined at all, will be able to put information in themselves. So just like many people have no trouble using a spreadsheet today, many people should have no trouble using a simple rule base. In fact, less trouble. Okay, what are some of the disadvantages of using rules, the cold, hard facts? Well, one is that every problem has some degree of control in it, has some degree of sequentiality. So you have this ideal that you're going to stick a bunch of rules in a big rule base, and voila, it all comes out all right. Doesn't matter what order they fire in. Well, of course it does matter. You have to take the, I'm trying to think of a good example. You have to open the hood of the car before you look inside to see what's wrong. So there are various methods of rule sequencing, and certainly no standard methods of rule sequencing, and I don't think people agree really on the cleanest way to do that, but that has to be done although it doesn't really have to be done in very small problems. That cannot be a problem because the rules themselves state clearly enough about what the state of the world looks like when they're supposed to fire, and then it's not a problem. It's when you have states of the world and they're talking about, I mean, you're talking about a big state of the world. So this rule says I fire over here and this rule says I fire over here. Well, how do they know which of those should go and do their job at the same time? But this brings us to the fact, what Ed had also brought up, is that there are no standards yet with rules. And so you don't have, for example, in conflict resolution, you don't have a little section in your documentation that says, this is how conflict resolution is done. Often it's left out, or if it's left out, or if it's put in, it's got different words, and so it's hard to figure out exactly what's happening. And then finally, most problems, particularly big, complicated problems, have some algorithmic portions to them. And if you're at all worried about running in a real environment, you're going to want to put any algorithmic code you can find into algorithms because they run faster. And also if they're not changing, if these are very static. And some people might disagree. This is somewhat, this is my opinion on this. But you're going to want to put them in algorithmic code. And the transition between rules is not yet standardized and is not often easy. So even when someone talks to you about an open architecture, oh, this tool has an open architecture, it can be called and it calls out to other things. Well, I mean, even when you do that in any other language, you try to call between two, you're talking about differences in data type representation and things like that. And so it's never an easy problem. It's also not terribly complex. But a good example of this is that the XCON system, which has, 7,000 rules, also has something like 300 external routines written in 7 different VAX languages. Well, you can imagine the kind of maintenance headache that is, that you need specialists in the communication between ops, the rule base, and these 7 different languages. I mean, that's not a small task. So those are things to think about. Okay, so that's it for rules. Any questions on rules? Using rules? Yes, I just about covered it. Another commercially popular and available knowledge representation are frames. And frames written about by Minsky, Marvin Minsky at MIT, in about 1975. And they also resemble what you who are familiar with object-oriented programming, they also resemble objects. The idea here is that it's a lot like a record structure. You have a named entity and a bunch of information about that named entity. So you have, frames have some name, they have what are called slots here, or characteristics or features or attributes, and then each of those slots have a value or values. So my example here, something I'm a little obsessed with at the moment, is that you have some bike, and you can have a type of bike. Let's say it's a tricycle, that's a value. So the slot is type, the value is tricycle. I have some make. This is a very fancy tricycle. It has 3 wheels. It has 0 speed. Or I guess it has 1 speed. 1 speed. It has extra. Does it have a basket? Does it have a bell? And I have some way of computing its cost. And the manufacturer tells me that. They say, well, you get a tricycle. If you get the deluxe version, you have. So you have some procedure there for computing the cost of that. Now, frames are not just static little entities that sit there and look nice. They also have some inference methods associated with them. And these 2 basic inference methods are attached procedures or inheritance. We'll talk about inheritance in a minute. First of all, just the attached procedures. You can attach procedures to slots that do particular things when values come or go, or when you request values from there. And so if I need a value from a slot and there doesn't happen to be one, so for example in some default, if I need some default, I can go off to calculate some value for that slot. If there can be a procedure, and you notice you can have these procedures on the same slot. You don't have to just have one procedure per slot. If I add a value to a slot, and a common example of this is error checking. If I add a value, I can go to make sure that that value satisfies a certain constraint. Okay? Similarly, if I remove a value, there might be something that I want to do. Now, all of these are daemons, which means that they are not going to fire until something happens in the slot and wakes them up. There can also be other procedures, just certain calculations that you do routinely for the value of that slot. You can do matching. You can have procedures that match to match certain frames with other frames to get values, similar values. So, for example, the computing cost is it's another procedure. If I have all the values needed to compute cost, I can compute it without requesting that value explicitly. The other way of getting a value is by inheritance, and this should have been on the following. This should be on the following page. Yep, sorry. Okay, so frames are related to each other hierarchically. So you have a bunch of frames. I can have a frame that represents a bike, and a bike is a class. So I say I have a general type of object. This is the type of object it is. I have several subclasses, and how classes and subclasses are related is in what their slots, in the slots that they have. And then, so here we have our class, or our type, and here we have subclasses. And I'm using this dotted line to indicate these are instances. So this Tom's bike and my bike both have values that are specific to an instance of a bike. And how these things are used together is that I can inherit values. So I can, if I need to find, for example, how many wheels my a racing bike has, well, I don't have to store that with both recumbents and racing bike and mountain bike. I can store that here. And you can also notice that in the bike template as the class, I could also have number of wheels, but I wouldn't go all the way to that level to inherit a value. So actually, let's see, this is a mistake. This was supposed to be on the same page so you could see it. Okay. Frames in a hierarchy can inherit values from slots and frames that are higher in the hierarchy. Okay, so although this template may have a slot value, I may want to get a value lower in the hierarchy that is more specific to my instance. Okay, simple idea, real powerful, and most often, I mean, frames, as you can see, have attached procedures and inheritance, and they can sit on their own. But you can also have hybrids with rules and frames, and the frames are the objects that you're reasoning about. So what we were talking about is a pattern, which could be as simple as a list. A pattern can also access a frame. Okay, and that's how you hold the data about your state of the world. Now let's move on quickly. We're actually running out of time. We have Blackboard systems which are becoming more, are not found in commercial systems, but certainly are used in systems other than commercial systems, and so there's a good sense that you may see them in commercial systems. And Blackboard systems are more of an architecture than a knowledge representation, a way of organizing an expert system. And what Blackboard architectures do are provide some centralized control to a number of knowledge sources. And think of this, it's a wonderful name for it because it's completely analogous to what it is, a Blackboard. Think of some project that you were on. You're working with you're a specialist, you're working with a number of specialists, but you don't really sit down in a room. You're working on one project that you all want to contribute to, but you don't sit down in a room and talk about it. Instead, you all work off in your own offices, and when you have a result, you come and you put it on the Blackboard. And you also, from that Blackboard, it's got a mind, this Blackboard, and it tells you some control information like, why don't you take this information and go work on it? I got this result from somebody else, and why don't you go off and see what you can do with it? Okay, so a number of knowledge sources that are specialized in certain tasks, and they place messages on the board and retrieve messages to work with input. The implementation of the knowledge sources is transparent to the Blackboard itself. So you can have, they don't have to have a uniform implementation. The example of this is the hearsay system, which was one of the earliest natural language systems, and it's a perfect example for the use of something like this, where you have a number of tasks that have to be done at different levels, but they have to be coordinated, so that if I'm getting some signal, a voice signal in, I'll have to do things like interpret the signal, and once I want to do all sorts of things like recognize syllables and recognize words. Of course, these have to be time-stamped, so then when I do recognize a syllable, I can say, in the sentence here, I recognize a certain symbol. Then when you have a set of syllables, you can recognize words and put together words, and when you put words together, you can put words together into phrases and word sequences. So a really, really good idea. Okay, two capabilities that are very important to expert systems. We're talking about heuristics. None of this is, but a good portion of the inferences you're making are not 100% certain in every single case. So you want to somehow represent what the uncertainty involved in your decision is. Some common techniques are either to ignore it, and a lot of the commercial systems do. They just assume that you don't have to worry about the uncertainty, or else there are some ad hoc methods, and these are usually structured from the domain itself. What does the expert think and these are some sort of probabilities, but they're not combined in a strictly probabilistic manner. You can also, so this is a rule from the Meissen system, which says that if I have some infection and I know the site and I know the suspected portal of entry, then I have a certain amount of evidence, and this is the amount of evidence that I have that the organism is bacteroides. And so I can combine these uncertainties in some predetermined fashion, but not necessarily probabilistic. Now, you can also use things like Bayes' theorem, and that's been tried in systems, and these are used. You take the prior and the posterior probabilities to weight the inferences that you make. The problem with that is that it makes all sorts of assumptions about the numbers that you can gather about those inferences that you're making, that you actually know what the probabilities are, some real probabilities. It's very difficult to know what real probabilities of things happening in the world are. And rushing right along, we're going to finish up right on time. Explanation, it's extremely important that an expert system be able to explain and justify its results. One is that you have people using this system that does things that they haven't seen computers do before. And you can't make this, they can't take the leap of faith, or shouldn't be asked to make the leap of faith. Also, for debugging purposes, you really have to know what's going on in the system, and also for knowledge acquisition. If this system can explain what it's doing, then it's easier for the expert or whoever you're getting information from to say, yes, in fact, that is the right way to go about the problem, or here's something you want to add. Now, the first explanation systems, you mostly use textual forms, and specifically, they were able to ask the questions, why? Why is the program asking me this question right now? And this will give you some, it will tell you, I'm looking for the condition in this particular rule. I'm looking at this particular rule because it follows this line of reasoning that I've been using. And how did it, if I have some final result, well, how did you get at that result? Now, graphical interfaces are playing a big part in being able to see what's happening. So you can see that the relationship of rules and conditions in a rule. So rather than having to say, I got it from this rule, which got it from that rule, I can just make up a tree structure that has, these are the conditions in the rules that contributed to this rule being true, and this rule turned out to be a condition in another rule, and these all combined to make another rule true. And so it's much easier for humans to see that graphically. You can also have the relationship of data entities. If we're talking about frames, you can see how things might have been inherited. And also, you can just have diagrams that reflect changes in the system. What if you have a bar graph that indicates the certainty that you have of a particular proposition that changes as the system moves and gives you some reason for that change? But the ideas that are central here are that you're going to get rule traces. If you have a rule-based system, you're looking for rule traces. What rule did I fire when? And you can also use some what they call meta-knowledge. Knowledge about what, so have special rules in the system that have information about why the system is doing what it is. Okay, so some conclusions. So we've looked at really the basis of all of those tools and shells out there. And even though these are simple, it takes a long time to implement one of them yourself. And it's much nicer to have someone else do the work for you and to just take it from there in a specialized domain. And so you want them to do things like develop a rule and frame structure and the syntax for those. You want them to develop some pattern matching capabilities, the inference methods, develop some method for uncertainty, although that's less common. And then particularly you want a nice environment sitting there. You want it to be able to do rule traces, you want it to do it graphically preferably, and you want some other kinds of debugging aids. Notice that when you do have someone else do it for you, it's not, and if you have experience with more than one tool, there's always a compromise. They never quite do it like you would have done it, but it's certainly worth the compromise in my opinion. The big win here is being able to separate knowledge and control. So you have some sense that this is a knowledge base, and future research is, let's say that this is a knowledge base that's not specific to a certain problem. Let's talk about this is just knowledge about a domain. Now I can solve several problems using that same knowledge base, and that's still in the future. And then, so finally, I see two big problems with implementing these systems. One is the challenge of representing your knowledge correctly. And this is, and I'm not talking about whether you use rules or frames. I'm talking how do you analyze your domain. And this isn't as much of a problem in a small system. It's a real problem in a system that you want to scale up, that you want to make bigger. Because as you add complexity, it's got to somehow fit in with the knowledge representation that you already have. And then the next big problem, which is what this course is really about, and what all these people are going to talk about, and it cannot be minimized how difficult this is, which is doing the project in an organization and making it successful. And so we're going to talk about some of those aspects in next Tuesday's lecture, the process of building. Any questions? Thanks.